Welcome. This podcast is going to focus on binary phase diagrams and is part of our metals unit in material science engineering. I'm Miss Mikesell and I'm one of the teachers at Eagle Crest High School. So our learning target for today's podcast is how can you read and interpret a binary phase diagram? And then secondly, what is the eutectic point on a binary phase diagram? So let's start by reviewing two of the things that we've already looked at. If we look at the crystal structure for various alloys that form, we can have either a homogeneous or a heterogeneous alloy. A homogeneous alloy has the same grain structure. That would be either a substitutional alloy or an interstitial alloy. Whereas a heterogeneous alloy has a different grain structure. This is a eutectic alloy and what we're going to be looking at as we study the binary phase diagram. So if we look at the homogeneous alloy and compare it to the heterogeneous alloy, can you see in the picture what the similarities and the differences are? Hopefully what you're noticing is for each individual grain of a homogeneous alloy, the grains are the same. This is pictured as a substitutional alloy where you have your alpha or your alpha or your blue component and your beta or your red component. And you have both of these substituting into the crystal lattice or the grain structure in each other's places, right? It's important to note that each grain of a homogeneous alloy would have the exact same percent composition. Homogeneous meaning the same, and each grain has the same percent composition. In other words, the component B that's substituting in is substituting into the grain structure of component A in the crystal. If we look at the heterogeneous alloy, we have a different grain structure. Hetero meaning different. This is a eutectic alloy, and we can see the grains are very different from each other. This grain primarily has alpha crystals. It's a solid solution that the main component is the alpha crystal, whereas this grain primarily has beta crystals. The main component is the beta crystal. I would strongly recommend that you draw these two grain structures into your notes with some color coding so you can see and visualize the differences between homogeneous versus heterogeneous. So if we look at homogeneous alloys, this is when we consist of a single phase. For an example, brass is a substitutional alloy where zinc comes in and substitutes into the crystal structure of the copper. And this is an example of a homogeneous alloy. Since brass is a substitutional alloy that is homogeneous, meaning it doesn't matter how much zinc is substituted in, it will replace the copper in the crystal structure, we can see our phase diagram. And as we've talked about previously, all alloys have melting point ranges instead of single melting points. And that's because as you make an alloy, those two different metals are changing phases at different rates. And so you get a range or a temperature, a low and a high temperature at which the alloy starts at and completely melts or freezes at, right? So if we dissect this graph, we can see that if our alloy was primarily component A, this would be its melting point. Its melting point would be temperature 5 over here in the graph. And that means that it melts at a single point because it is a pure substance, only A. Whereas if it was a pure substance that contained only metal B, it would melt at this much higher temperature, temperature 2 on the graph. The moment we start to blend the two metals A and B together, we see that instead of a melting point, it has a melting range. It starts to melt at this temperature and finishes melting at this temperature. And as we change the composition and blend more of metal B in with metal A, we see that the range, the temperature at which it starts to melt and completely melts, changes. In this case, metal A and B are completely soluble in each other. However, heterogeneous alloys form when there is two or more phases, when one of the metals is only partially soluble in the other metal. An example of that could be this copper and gold phase diagram that we see below. Okay. So obviously this diagram looks a little more complicated than the one we see on the left, and that's what this podcast is going to focus on. We're going to be looking at how we read and interpret a binary two or more phase diagram. So let's get started. You should be filling in your guided notes that supplement this podcast. It will help you kind of organize the information and ideas. The binary eutectic phase diagram explains the chemical behavior of metals that are not completely soluble in each other. So the solubility changes depending on the percent composition, how much of metal B is added to metal A. And if we consider what happens when we change solubility, when two metals are completely soluble in each other, we get the homogeneous substitutional or interstitial alloy, which creates the grain structure that we saw previously at the start of the podcast. When metals are partially soluble, we get a heterogeneous alloy. In other words, as we talked about at the beginning of the podcast, each grain has a different structure. This one is mostly the solid alpha component. This one is mostly the solid beta component, right? Heterogeneous or a eutectic alloy. And if the metals were completely insoluble in each other, it would be a mixture of pure crystallites where each grain is composed of the different metals. That's not going to happen in this podcast. We won't be looking at this because for a binary phase diagram to occur, you have to have partial solubility. So this type of crystal structure we will not be looking at further. So alloys have melting point ranges instead of a single defined melting point. They are mixtures, and the percent composition of each substance determines their properties. The x-axis on this graph shows the composition by mass of each of the two components in the mixture. We can call those alpha and beta, or A and B. So we can see that on this graph, if I'm looking for where I have 100% of component A, that would be this far vertical boundary on the left side of the binary phase diagram. At this point, I have 0% of substance B, which means it would be 100% of substance A. So the left-hand boundary of the binary phase diagram indicates where there's 100% or it's a pure substance A. The right-hand boundary would show where it's 100% of component B, a pure element, and 0% of component A. I would strongly encourage you, as you start to read and interpret binary phase diagrams, to do the first thing is to label in where you have 100% of A and 100% of B on your diagram so that you know how to read your x-axis. That's a critical first step. The y-axis on a binary phase diagram shows the temperature of the mixture in degrees Celsius. It can also be in Kelvin or Fahrenheit, but typically in science we use Celsius, and so that's the most common that you'll see. So again, the y-axis is simply showing the temperature of the mixture, and generally that's portrayed in degrees Celsius. This top section in white on this diagram is showing where both components in the mixture are melted, and so it is a single mixture, right? This is the region, the white section on this diagram is showing where both components are 100% liquid. In other words, your mixture is completely melted, all melted. The liquidus line is kind of the V line that separates the completely liquid section from what we call the slushy zone, where the material contains both solid and liquid components. Since alloys melt over a range of temperatures, instead of acting like a pure substance with a single defined melting point, there's going to be a time period where the mixture, as it melts, will contain both solid crystals as well as liquid melt. So the liquidus line is the boundary between the entirely liquid section and the slushy zone, where you have some solid and some liquid as it's completely melting or freezing. The melting point temperature is the temperature at which the substance melts. If we're talking about a pure substance, pure substances have a melting point, a temperature at which the solid changes into a liquid when heat is applied. So if I'm talking about component B, if I have 100% component B or purely metal B, my melting point temperature would be right here where the liquidus line intersects with that right-hand boundary, or where there's 100% B. The temperature right here, temperature at B, at this point would be the melting point temperature of substance B, approximately 1,485 degrees Celsius. Can you identify what temperature 100% component A would melt at? What's the melting point temperature of substance A? Hopefully you're looking to the left-hand side of the graph where there's 100% of metal A. So that would be this leftmost boundary of the graph. And going up to where the liquidus line intersects, this is where things are 100% melted. So where we see temperature A, that would be the melting point of substance A, it's somewhere much greater than 1300 and a little bit less than 1400 in temperature. I estimated 1,390 degrees Celsius. Hopefully your estimate was close to mine. All right. The slushy zone is where the material contains liquid mixture and solid crystals of both substance B, the beta crystals, or substance A, the alpha crystals. On our diagram shown in the notes, this green section is the slushy zone where we get liquid melt and beta crystals, solid crystals of metal B. Where would the slushy zone be for metal A, where we'd have solid crystals of metal A along with liquid mixture? Hopefully you told me that was the yellow section. Again, this yellow section would be where you have solid crystals of metal A and some liquid mixture still, because again, alloys melt over a range of temperatures, and so they're going to have a slushy zone. And the solidus line shows the freezing point temperature, the temperature at which a liquid changes into a solid when heat is removed. So the solidus line is the freezing point temperature. This is when your mixture or your alloy completely freezes and solidifies, turns into a solid. And so on this graph, that temperature is approximately 1,240 degrees Celsius. If you're like, wait a minute, did she just say 1,240 degrees Celsius? I did. I know that when we think of freezing point, we think of really low temperatures because we're thinking about things like water that freeze at 0 degrees Celsius. But if we're talking about metals, metals solidify, they freeze at much higher temperatures than what we're used to in our everyday life. So the temperature at which a metal solidifies, becomes completely solid, and freezes happens at a temperature of 1,240 degrees Celsius for this system. And if we look, the blue section of this binary phase diagram represents when the alloy is a complete solid. So our mixture or our alloy is completely solid crystals of both components. Again, the melting point range is the temperature at which your alloy melts. So if we're talking about a alloy that is 20% B and 80% A, it's going to start to melt at the solidus line, 1240 degrees Celsius, and it will finish melting at the liquidus line, 1360 degrees Celsius. What's the percent composition of a substance that melts completely at a temperature of 1400 degrees Celsius? To answer that question, we would need to go to the y-axis to 1400 degrees Celsius. We'd need to go where it completely melts, the liquidus line, and then we need to trace down to the x-axis to get the percent composition of the alloy at that location. So if it completely melts at 1400 degrees Celsius, it would start melting at the solidus line, and that occurs when we're at a percent composition that's above 70 but less than 80% component B. I estimated it at 76% B and 24% A. Okay, this special location on the graph right here where the liquidus line V's down and intersects with the solidus line is known as the eutectic point. And the eutectic point is the location where all three phases exist simultaneously. At this point, you have both alpha crystals, beta crystals, and liquid. This is the point in which the mixture of substances has a melting point lower than any of its components. You can see on a binary phase diagram that alloys always have lower melting points than the pure substances that they're composed of. The melting point temperatures of the pure substances are the higher temperatures on the graph. As something is mixed and becomes an alloy, the melting point range, the temperature at which it melts at, is lowering. And the eutectic point is the lowest point at which that mixture or that alloy melts at. It's lower than any of its components. And notice it is a point. So at the eutectic, even though it is an alloy and it's a mixture of two different metals, it's acting like a pure substance and melting at a single defined temperature. The eutectic point temperature would be the temperature of the solidus line, the freezing temperature, because it's intersecting. This is when the liquidus line intersects the solidus line. It's the temperature at which the mixture of two substances produces the lowest melting point temperature. Again, note that it's not a range. The eutectic point is when our alloy is acting like a pure substance and melting at a single defined temperature. And the eutectic composition would be the percent composition of the alloy at which it acts like that pure substance. So it's a mixture of substances having a melting point lower than any of its components. For example, in this example, the eutectic composition happens to be 50% A and 50% metal B, or 50% theta or alpha and 50% beta. But that's generally not the case. Most of the time, the eutectic composition is a percent composition that is not 50-50. So now we're going to transition into how the crystal structure changes at these points along the binary phase diagram. And you can see that the binary phase diagram that I'm looking at has a section that wasn't present on our simplified graph right here. On our simplified graph right here, our slushy zone were these triangular wedges, and we didn't see the solvus line that was present because it was simplified. So let's start by looking at what that means. If I want to orient myself to this graph, my pure substance would be 100% alpha at the leftmost boundary, and it would be 100% beta or metal B at the rightmost boundary. And the solvus line represents the section where the solubility goes from completely soluble in each other to only partially soluble in each other. So if we remember, if something's completely soluble, it forms a homogeneous alloy, whereas if it's partly soluble, it forms a heterogeneous alloy or the eutectic alloy. So the solvus line, again, separates the homogeneous solid solution from the field of several phases which form by incongruent melting, in other words, partial solubility in each other as they melt. And where you see the alpha crystal right here, this section is going to be where you would get a homogeneous substitutional alloy. Meaning if we look at the crystal structure, it's going to be homogeneous. The alpha phase will have a crystal structure like pure A, and it will have some of the beta crystals substituting into the crystal lattice. So you're going to get a homogeneous substitutional alloy. In other words, a crystal structure that looks like this. We could make those purple and green instead. The moment we go past the solvus line, right here, we're getting into partial solubility. So from here all the way across, we have a heterogeneous or eutectic alloy until we hit the next solvus line. So all of the crystal structure that forms right here is going to be a heterogeneous or eutectic alloy. And that is because we are only partially soluble. So again, we would see a crystal structure each grain where the grains are going to be different. And this one is composed mostly of alpha crystals, mostly of beta crystals. They'll have different percent compositions to each other. And right at the eutectic, you get this really cool layered crystal because you have your alpha crystal melting and solidifying, your beta crystal melting and solidifying, and some liquid mixture all occurring simultaneously. And so you get this really cool, what we call eutectic composition. As you move closer to the eutectic, you can see that you're getting less and less solid alpha crystals, and it's getting closer and closer to that eutectic composition. And as you go back towards the solvus line, you can see it's more and more solid beta crystals appearing in solution until eventually it's entirely solid beta crystals as you cross the solvus line. So let's look at the lead-tin binary phase diagram, where we can see this play out in terms of the crystal structure. To orient ourselves to the diagram, I'm going to just ask you a couple of questions. Which boundary on the graph would represent 100% lead? The leftmost boundary of the binary phase diagram or the right? If we're looking for 100% lead, hopefully you said the leftmost boundary, because right here we have 0% tin. Right here we have 100% tin. So if this is 100% tin, then this leftmost side would be 100% lead, 0% tin. Okay, what would be the melting point temperature of tin? If we have a pure tin, SN, what would its melting point temperature be? Hopefully you told me somewhere between 200 and 250 degrees. Your estimate should fall between those because we should be looking for 100% tin over here on the right boundary, going up to the liquidus line where something melts. And if we go over here to our y-axis, we should see that occurs somewhere above 200, but less than 250, probably around 230 degrees Celsius or so. Okay. All right, next question. What is the freezing point temperature? In other words, what's the temperature at the solidus line? Hopefully you told me that was 183 degrees Celsius, because we can see the Solidus line extends from right here, the melting point of pure tin, down, runs horizontally across the graph at 183 degrees Celsius, and then would extend up to right here, the melting point of pure lead. 183 degrees Celsius is where the Solidus line, or freezing point temperature, of our alloy would be. Can you identify where the alloy would be mostly solid alpha crystals with some liquid melt? Let's call this section 1, 2, 3, 4, or 5. Hopefully you told me that was at section 5. At section 5, we're in the slushy zone, and we'd have mostly solid alpha crystals plus some liquid melt, because our alloy or percent composition is going to be melting over this range of temperature through this region. Okay, again, if we call this 1, 2, 3, 4, and 5, where would our substance form a homogeneous, solid, substitutional alloy? Hopefully you said that would be in section 4, where the alpha crystals are marked. Again, this is our solvus line, where the solubility changes and becomes insoluble. And through here, we get a homogeneous or substitutional alloy. As we enter this section, we get the heterogeneous or eutectic alloy. And over here, we would get the homogeneous alloy of our beta or B crystals. All right, let's click into the animation and start to look at the crystal structure that would form in these regions. So right here, we're in the completely liquid zone, where our substance is entirely liquid. So we can see that the crystal structure would be 100% melt and liquid. And if we roll into this section, we should expect solid crystals of alpha plus some liquid melt. That makes sense. If we roll into this section, we should expect solid crystals of beta plus some liquid melt. And again, if we go into this section, we should see homogeneous beta crystals. This is the section where it is completely soluble in each other. And if we go into this section, we should see homogeneous alpha crystals. As we go across the graph now at the solvus line, we're going to see that our substance becomes only partially soluble in each other. That's why we have a binary phase diagram. And so as I go across the solvus line, I'm going from a homogeneous alloy to a heterogeneous, and I'm going to have mostly alpha crystals with a little bit of beta crystals. As I move across and the percent composition increases, you can see that my alpha crystals are getting smaller, and I'm getting more of the eutectic composition. Alpha crystals even smaller, more of the eutectic composition. Even smaller. And as I get towards the eutectic, notice I'm directly below the eutectic, and so I'm getting entirely eutectic crystals. And now as I move to the right, we're going to see that I'm going to get more solid beta crystals, which are going to grow progressively larger into that crystal structure. And eventually, as I cross the solvus line, we're going to be entirely beta crystals. I hope this podcast was helpful. Thanks for watching.